Good afternoon, everyone. It's a great pleasure to speak at FIO this year, and I was invited to talk about our work in collaboration with the A-chip team on inverse design on-chip laser-driven particle accelerator. So let me start by reminding all of you that when someone mentions an accelerator, we usually think about these very large-scale structures, such as the SLAC linear accelerator, which is a few miles long and sits on top of the hill above Stanford, or this CERN accelerator, which is even larger and leads to larger acceleration energies of electrons. But of course, there are many other smaller scale accelerators, and actually majority of accelerators today that are in use are the ones that are used in medicine, and they accelerate electrons to lower energies on the order of mega electron volts, but they're used in hospitals throughout the world or even for scanning of shipments. So in our work, we're trying to build more scalable and more practical accelerators that would also be more accessible to everyone. And we're particularly at the moment focusing on these mega electron volt scale accelerators, although we also hope that our work would eventually be scalable to giga electron volt scales or even larger. So what is the main idea behind the accelerators that we're pursuing? Majority of accelerators today are based on microwave or RF acceleration of charged particles, and they're so-called oscillating field accelerators. So basically, they're implemented by connecting a lot of these microwave cavities and coupling microwave or RF input, which oscillates at a particular microwave frequency. But the system is designed in such a way that for an incoming electron, its velocity is matched to the dimensions of this accelerator and also oscillation frequency of the field, so that as an electron traverses through this accelerator, it always sits at the same phase of the field, which leads to net acceleration. If this was not all properly matched, then we would also see electron accelerating and slowing down, so we would not really achieve large net acceleration. And these tabletop accelerators that would, for example, be used in medicine would look something like this. These are radio frequency cavities. But of course, in larger scale accelerators, you have to scale and cascade even more of these stages. So this state-of-the-art accelerators relied on microwave or radio frequencies. And of course, if you just look at the scale of the electromagnetic wave spectrum, by going from microwaves or radio waves to optical frequencies, we can actually scale down sizes of accelerator dramatically by a factor of about 10,000 relative to state-of-the-art. And initial work on this was done around 6-7 years ago by Bob Byer's team at Stanford in collaboration with groups at SLAC. And in that work, they used quartz platform with these edge structures in order to show that you can use laser fields in order to accelerate electrons in smaller structures. Of course, in that proof of concept work, it was just shown that this could be done using laser frequencies, optical frequencies, and using dielectrics, but it was not really done in a scalable way that would lead to mega electron volt or larger energies of electron and practical systems. Which is why about 5 years ago, led by Bob Byer, shown here, and Peter Homohov, we started on-chip particle accelerator collaboration. This is a large collaboration funded by Gordon and Betty Moore Foundation and includes many groups from around the world, primarily from the US and Germany, but we also have collaborators from other parts of the world, including Japan. And we're actually working on building a scalable on-chip accelerator, which is also useful for practical applications, and that would reach the range of energies that could be used already today in applications in medicine or even eventually in high energy physics experiments. So the whole idea for achieving that is to implement on-chip particle accelerator using dielectric structures, semiconductor structures, and integrated photonics in a scalable manner so that we can, like in traditional accelerators, integrate a lot of stages, but on a much smaller scale. And by using frequencies of optical frequencies, we should be able to actually reduce the size of the accelerator by a factor of around 10,000 relative to state of the art. So for example, SLAC accelerator, which is a few miles long, could in principle be integrated onto a single silicon wafer. Of course, you cannot really just shrink all the components of accelerators that operate at microwave or radio frequencies by a factor of 10,000 and obtain a functional accelerator, because we plan to use optical frequencies, and metal would absorb a lot at optical frequencies. So everything would have to be redesigned in order to achieve the right behavior. And redesigning this is not a trivial goal because there are a lot of elements that need to be designed that we don't usually work on in optics. We also have to work with large laser intensities. We have to worry about damage to the structure. We have to design the structure in such a way that field is in phase with the incoming electron and so on. And how do we achieve that? Brute force design would really not be a tractable problem here, which is why we decided to use inverse design in photonics. And just to remind you, inverse design is basically relies on combining classical optimization techniques with photonics design in order to build photonic structures for a particular goal. And we have been working on it for a long time, for about 15 years. We have shown that we can design structures that are much more efficient than state-of-the-art, more compact, and also robust to a variety of errors and environmental conditions. But we can also implement many new functionalities. And these structures here are examples of some of the devices that we implemented, wavelength splitters, for example, in silicon. But I'll show you today how you can use this approach to implement on-chip particle accelerator. And since we've been working on this for a long time, we've also implemented software suite, which we call SPINS, Stanford Photonics Inverse Design Software. Quite a few companies and research groups are using it. It's available for licensing from Stanford, but we also have open source basic version if you're interested in playing with it, which is available for download on GitHub. And our recent review article published in Applied Physics Reviews describes this software and our approach in greater detail. What is very important for on-chip particle accelerator implementation is that photonics inverse design is also fully compatible with foundry-based fabrication, because if you were to implement accelerator, you have to integrate many stages with high precision. It would eventually occupy a few inches of a wafer, and this is beyond the scope of sizes of structures that we're fabricating in university facilities. Over the past few years, in collaboration with various foundries, we have shown that inverse design is fully compatible with foundry-based fabrication. We have collaborated with several major foundries. Here I am showing you our initial work done in collaboration with John Bowers' group from UC Santa Barbara and employing AIM Photonics Foundry, where we have shown that the quality of structures, inverse design structures fabricated in a foundry, is fully on par with our inverse design structures fabricated in Stanford fabrication facilities. The process is exactly the same, whether you're using a foundry-based fabrication or university facility. You start with your optimized design, which includes fabrication constraints of a particular fabrication facility you are using. You develop designs, which you can send to a foundry or as a GDS file to your electron beam writer, and beyond that is just a traditional fabrication. And here is a comparison between our structures, three channel wavelength splitters fabricated in silicon using Stanford fabrication facility, same device fabricated in AIM Photonics, and theoretically predicted behavior for 3-channel wavelength splitter, and actually experimental demonstration of a 3-channel structure measured over many devices on a chip fabricated in AIM Photonics. So what you see here are not error bars. These are just superimposed transmission plots for multiple wavelength splitters fabricated in AIM Photonics. You see that they all line up on top of each other, which is excellent. We don't really do any post-fabrication tuning of the structures, so they're really robust to fabrication errors. So inverse design, to summarize, allows you to implement new functionalities, robust structures to the environment, high efficiency structures, and is fully compatible with foundry-based fabrication. And all of these are extremely important for on-chip particle accelerator. So going back to on-chip particle accelerator, this is a very new functionality that we have to design. And it's very different from designing a wavelength splitter. So how do we approach this problem? Well, the main goal, the main property that you need to optimize in an accelerator is a so-called acceleration gradient. You want your electron, incoming charged particle, to gain maximum energy over a short distance in the structure. But structure also has to be designed for this electron, having in mind its initial velocity. So each stage has to be designed for a particular initial velocity of the electron. That's exactly what we do, and of course it has to be integrated with the vacuum waveguide for the incoming electrons so that the electron can propagate. You also need passive photonic structures to couple your laser, propagate, and so on, and I'll show all of that later on. But here I'm addressing the key portion of the accelerator, which is waveguide for the electron itself, and maximized vacuum waveguide, optimized in such a way that it provides the maximum acceleration gradient. So how would you do that? I mean, like in traditional RF accelerators, you want your electron to be in phase with the oscillating field so that it is never decelerated, so that it's always accelerated and reaches the maximum energy per unit length. And you can try to design this problem by hand. You can say, well, I have some piece of the electric. I'll couple my laser from a side into the structure, same as you would do in RF accelerators, and then optimize this region here, the electric constant in this region here, where electron would be coupled to a vacuum waveguide, right? Optimize the electric constant of this region here so that you always your electron is always in phase with the oscillating electric fields and receives maximum acceleration. So brute force, you can address this problem by pixelating it into something like 100 by 100 nanometer pixels, which are pretty coarse, but even if you pick these coarse pixels and pick 2 micron by 1.5 micron design area here, you will have a lot of possibilities for the resulting structure. And if you try all the combinations of pixels, being silicon and air, it turns out that you have 10 to the power of 90 of possible devices here, and you would have to simulate all of them and see which one of them provides maximum gradient and maximum acceleration. So finding optimal solution via this brute force search is not a tractable problem, and that's not how you should design the structures. So what we do instead is gradient-based optimization, which means that we're still solving the same problem. We still have this enormous parameter space consisting of 10 to the power of 90 structures, or even more, because pixels should be smaller than 100 by 100 nanometers. But instead of brute force searching, doing this blind brute force search through this enormous parameter space, you're just guided by the physics of the problem. You basically look at which pixels would contribute to the largest changes in the gradient that you're trying to optimize. So what you have to do is you have to look at the derivative of the acceleration gradient relative to the electric constant of the structure. And that provides the sensitivity of the acceleration gradient relative to the underlying electric structure and tells you which pixels you have to change in order to make maximum changes to the acceleration gradient for your particle. That's exactly what we're doing. This is basically how optimization works. That tells you how you can travel through the whole enormous parameter space using gradient descent techniques. follow the steepest descent until you get to some local optimum. Of course, calculating derivatives of the acceleration gradient relative to the underlying electric structure is quite consuming in terms of the computational resources and time, which is why we don't really do it manually. Instead, we use adjoint optimization. Adjoint optimization is a clever trick which allows you to calculate these gradients, derivatives of whatever you are optimizing, in this case, acceleration gradient for the particle, relative to the electric constant from just two simulations. That gives you the derivatives everywhere in space. You do forward simulation, backward electromagnetic simulation, which is adjoint simulation. And from these two simulations, you can actually calculate gradient of acceleration gradient, derivatives of the acceleration gradient everywhere in space. And that tells you exactly which pixels you need to flip in order to optimize acceleration gradient for the particle. And this movie here shows you how we're doing that. As we're optimizing the structure, permittivity distribution for this accelerator stage changes, and at the same time, accelerating fields are also changing, and you are obtaining the right distribution of accelerating fields inside of this vacuum waveguide where electron would pass. So that's how we do the problem. The resulting structure is quite non-intuitive. As you can see in this background behind me, it's not something that you would come up with on your own by hand, but computer optimization leads to this structure that looks like a beautiful abstract painting and leads to maximum acceleration gradient for the incoming electron. Of course, everything is optimized for the incoming electron at the right energy for our system, and then you can optimize for a different incoming energy in another stage. And if you had a different electron source, you can re-optimize the structure for that particular incoming electron energy. So on the left, you see fabricated optimal design in silicon on insulator. Electron would traverse through the vacuum waveguide at the center. This is superimposed with the electric field distribution for the incoming electron with 83 kilo electron volts energy, which it has in our system. It would be completely in phase with the electric field concentrated inside of the vacuum waveguide. Where coupling field through grating coupler, as I'll show you in a moment, from a side of the structure, it propagates through the slab waveguide, reaches this region, and that's where the interference with all these complicated optimized structures leads to the right electric field distribution and field buildup inside of the vacuum waveguide that would lead to a maximum acceleration gradient for the incoming electron. So that's the optimization part and inverse design part of the actual stage of the accelerator. And what I'm showing you here is just a single stage of the accelerator, which is 30 micrometers long. It's still 10,000 times longer than in the stage in the traditional accelerators. But of course, you still need to cascade hundreds or thousands of these stages in order to build the full accelerator, which is not a big problem here because each stage is 30 microns long. So in few inches of a silicon wafer, you can stack up sufficient number of them to get to mega electron volt acceleration. Apart from the stage of the accelerator itself, there are other optics components that you need to design. And one of the key components are grating couplers. Of course, we use grating couplers many times in our photonic integrated chips, but this is a very different type of grating coupler because you need to couple short laser pulses that have large bandwidth, and that's not what we typically have to deal with in optoelectronics. And on top of that, you also want to design this grating coupler to minimize your laser-induced damage. So you want to minimize concentration of electric field inside of your semiconductor so that you don't really induce the laser damage. And that's what we do. We designed broadband grating couplers. You can achieve even higher coupling efficiencies than what I'm showing here, but for simplicity, we just etch them fully through the silicon layer, so they're almost vertically symmetric, which means that the loss would be limited to 50%. But in future iterations, we will make higher efficiency designs that we have where we break symmetry vertically even more. So we couple through these grading couplers, we go through the slide waveguide all the way to the accelerator and measure acceleration there. So the full system would look like this. This is the input coupler for your laser. Everything is placed inside of the vacuum system. You have 83.4 kilo electron volt electron beam that is coupled to the vacuum waveguide. Field buildup would read to the right pattern that accelerates electrons, and then you have magnetic spectrometer at the output where you measure acceleration. And of course, you can cascade many stages on the chip, but in our initial work, we just demonstrated a single stage of accelerator, which is 30 micrometers long. Scanning electron microscope image is shown here. You have to etch out massa so that your electrons can access the structure. And the pattern that we optimized is in this region here. Everything is 30 micrometers long. Electron beam comes from the converted electron microscope, and magnetic spectrometer is at the output. Here is how the setup looks like. The little chip goes inside of this. Of course, you have electron source. This is converted column of electron microscope. Sample, which is not visible, would be in this vacuum system where we're performing the experiment. And going back to the experiment itself, once you put everything together, we actually measured acceleration gradient that exceeds 30 mega electron volts per meter. This is on par with microwave and RF accelerators. The size of the accelerator itself is reduced by a factor of 10,000. This comes from the fact that we use laser frequencies instead of RF and microwave sources. And this accelerator stage is 30 micrometers long, which means that on a single silicon wafer, you can easily integrate 100 or 1,000 of stages. So here is the measurement. With laser off, if you pass electrons through this structure without input optical field, they would just exit this stage of accelerator with the same energy that they had initially, 83.5 kilo electron volts. When you turn laser on, you see clearly that you accelerate electrons, and you accelerate them by about a kilo electron volt within this stage that is 30 micrometers long. And when you calculate gradient, when you divide that energy gain that you're getting per 30 micrometers of length, that corresponds to a gradient of 30.5 mega electron volts per meter. And that's comparable with state-of-the-art accelerators that are used for practical purposes. Of course, it could be done even better than this. So how does this compare with other on-chip laser-driven particle accelerators? I should mention that all of the previous accelerator demonstrations, which include optical structures, didn't really represent integrated accelerator demonstrations. So they are not really scalable to multiple stages of accelerator, which you need for practical applications. They just showed that you can concentrate the electric field around some structure and accelerate particle that is passing there, but you couldn't really cascade these elements as you could in our structure, in our on-chip particle accelerator, in order to reach useful acceleration energies. So we're here at the bottom. The previous result that was done at UCLA, measurements were done at UCLA in Peter Masumechi's group, but they employed same structures that were used in initial Stanford experiments by Bob Byers' group, demonstrated acceleration gradient of 850 mega electron volts per meter. That's improvement by a factor of about 4 relative to the initial Stanford experiment, simply based on different excitation. It was the same quartz structure, but again, this is not an integrated structure. It's not something that could be scaled. And we could reach the same range of acceleration gradients in our structure with the ability to cascade many stages together. So that's quite exciting. We have a gain of about kilo electron volt per 30 micrometers. How do we get to larger gradients? We're optimizing gradient couplers, also optimizing design. We're confident that we could actually scale gradients by an order of magnitude or even more. But even with the current gradient of 30 mega electron volts per meter, we could integrate 1,000 of the current stages and get to mega electron volt energies. 1,000 stages would occupy only something on the order of 30 millimeters of chip. And that's certainly doable on silicon wafers. So even current result is completely scalable, but it could be optimized further. And of course, to get more energy gain, you have to build multi-stage accelerator. That's only possible with our current demonstration. It's not possible with the other previous demonstrations because they're not in integrated configuration, but we don't really plan to do that using our university facility. Instead, we plan to do it using foundry-based facility, which is of course possible because everything that we do is fully compatible with foundry-based fabrication. We work with silicon wafers. We use inverse design, which we've shown is fully compatible with foundry fabrication. And in fact, we already are collaborating with foundries and sending multi-stage accelerator designs. And these are some of the recently received chips from the AIM Photonics, which include multi-stage accelerators. We're quite excited about this, and we're starting to perform some measurements on these multi-stage systems. So hopefully we will soon have some exciting results to report on multi-stage acceleration. So in summary, we can use photonic inverse design to optimize laser accelerators, laser-driven particle accelerators on a chip. We have already demonstrated single stage of accelerator, which is fully scalable, compatible with integration. We have 30.5 mega electron volt per meter acceleration there. We use lasers at frequency 2 microns for that experiment, but in future work we'll probably move to 1.5 micrometers just because of the availability of equipment. Again, we use infrared frequencies for this work and silicon photonics. And we are now working in collaboration with foundries on multi-stage accelerators. We're confident that in the next few years, we will get to mega electron volt acceleration, starting with just simple sources, which are converted scanning electron microscopes with electron energies that are sub 100 kilo electron volts. So that's the goal. That's where we're going. We think that we will certainly pretty soon reach the range of energies that are useful for medical purposes. And beyond that, it would be quite exciting to see whether we can reach a range of energies that are interesting for some physics experiments. Let me thank our funding. Gordon and Betty Moore Foundation has supported this on-chip particle accelerator work over the past 5 years. And this is the team, this is part of the A-chip team from Stanford that worked actively on these experiments that I described today. The team is led by Bob Beyer, Olaf Solgaard, my colleague from electrical engineering, Joel England from SLAC, my postdoc JP McLean, Neil Sapra, my graduate student who recently graduated, Kiel Young, my postdoc, my student Logan Su, postdoc Dries Verkruze, graduate student Rahul Trivedi, and team members from Olaf Solgaard's and Bob Beyer's group, research scientist Ken Liddell, who did some of the earlier experiments with on-chip acceleration, Dylan Black, who performed together with Ken Liddell electron acceleration experiments, and Yu Miao from Olaf Solgaard's group, who's also worked actively on fabrication. Thank you very much for your attention.